Okay, Assalamu alaikum. Today, today our topic is Michelson interferometer, which is very important topic, and this this experiment proves the wave nature of light, and this is also called a device which is used to measure the distance, with high accuracy or precision, with high precision and wavelength of light. The experimental setup for the Michelson interferometer is that we have a source of light, and then in front of source of light we have a partially reflecting mirror from one side, and the second one was a glass, and then we have a mirror, reflecting mirror, and another mirror is placed above the partially reflecting mirror, and this is M1 and this is M2, and we can place here eyepiece to observe the phenomena. Okay, now how this experimental setup works: we have a source that emits radiation or light. This is the light ray which is moving towards the partially reflecting mirror, and this light is monochromatic. Why we are monochromatic light here? Monochromatic light is used to study the interference pattern clearly. Otherwise, if we use the white light, so we cannot observe a clear interference pattern. So this is monochromatic light source. Okay, now we are considering here one ray of light which is moving towards a partially reflecting mirror, and this light ray enters in the medium and then reflects some part of it, and some part of it refract. Then this reflecting part goes up to the mirror 1 like this, and the second part of this light moves straight and enters in the glass that is also called compensating glass. It is a plain glass to maintain the potential difference, part difference, 0 here. So this light ray enters in this medium and then emerge out from this and goes straight to the mirror 2. Now these two light rays, which are one which is moving towards M1 and the one which is moving M2, these two light rays follow the same path after reflecting M1 or M2. Then they come like this light will come back and follow the same path and comes down in the eyepiece. Then this light ray also comes back after reflecting and follows the same path, then it also enters here. So we can consider it 1 and this is 2. So this was 1 and this was 2. And now these two waves shows the interference because they have the same wavelength, same frequency. There is no change in anything, and we are maintaining the path difference here, so we get the interference pattern here. Interference pattern is that when two light waves meet at a point with their crest to crest and trough to trough, so these two light waves superimpose and become a large, when have a large amplitude and a bright fringe called, so we get a bright fringe here. we get a bright fringe here. Then, so this is the bright fringe we have got from this. So if I remove this M1 mirror, it is also called movable mirror. So as I shift this mirror upward by the distance lambda by 4, so what does happen here? So the light which was coming to the M1, now it will have to cover a distance more than previous. Now light will cover lambda by 2 to move up, and then the lambda by 4, sorry, the light will cover lambda by 4 to move up and lambda by 4 to come down. Then this lambda by 4 plus lambda by 4 becomes lambda by 2 for the light. Then if there is a path difference of lambda by 2 between these two waves, so we get the dark fringe here instead of bright. This same pattern we can follow, and increasing the distance, the fringes become white, then dark, then white, then dark, then white, then dark. So it shows that the Michelson interferometer is proving that the light has a wave nature, and we can measure the wavelength of the light here. If we are placing in the distance, we can assume that if first we observe that the path difference is 0, means from this partially reflective mirror the distance from M1 and the distance from M2 are same, so path difference is 0. But if I move the mirror up, I can consider here rough values like 2 centimeter 2 centimeter, and the fringe was bright, then it is dark now. So we know that after bright there is a dark, so path difference is lambda by 2. But we moved the M1 lambda by 4, because we know that light will cover lambda by 4 to go up and lambda by 4 to come down. So we are moving mirror lambda by 4. If if the distance was 2 centimeters, so we can multiply this distance by 4, that it becomes 8 centimeters. So we can say that the wavelength of the light is 8 centimeter. We are considering here some values, it is not actual values here. And this device measures with the high precision, means the least count of Michelson interferometer we can consider, that is 400 nanometer. So it can measure up to 400 nanometer. So this was the experimental setup done by Michelson and proves the wave nature of light. I hope this video cleared your concept related to the Michelson interferometer.